Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to continue our task or our objective of looking at text clustering and topic modeling methods in the broad field of natural language processing. In the previous lecture, what we did was we used or we understood a framework which is called as BERTopic. Let me encode this with a different color right now. So the topic which we understood in the previous lecture is called as BERTopic, and what it does for us is that it helps us in a task called as topic modeling. So we have embarked upon this task of looking at research papers or preprints which have been published on ArXiV, especially in the domain of computation and language. We have looked at a data set which has 45,000 abstracts, and our goal is to cluster these abstracts based on common topics. So if there are a huge number of abstracts in the field of sign language, they'll be in one topic. If there are a lot of papers in, let's say, generative AI, they'll be in another topic, so on and so forth. So our goal is to first make clusters and then assign topics to every clusters. So 2 lectures back, we looked at how to make these clusters itself. We looked at a 3-step process which started with taking the documents and converting them into embeddings. The second step is to reduce the dimensionality of the embeddings by using a method called as UMAP. And the third step is to use a clustering algorithm to make these clusters itself. Now here we can see that the documents have been grouped into clusters. That's great, but still not very useful for us because we don't have the names or the topics of each cluster. We don't have, let's say, the title for every cluster, and that's where we need topic modeling. We need to go from these clusters to, if I just hover over each cluster, I should know what that particular cluster represents. If this is a cluster of all the papers or abstracts which talk about sign language, it should be written over there. Then it will be truly valuable for me, and that's where BERTopic comes into picture. So we saw that there are 6 overall steps for the topic modeling process in the previous lecture, and those 6 steps are: first, of course, you take the documents and embed them into a vector space. The second is you put them into a lower dimensional space using UMAP, and third, you form the cluster. So the first step is clustering, which we already saw, and then what you do is that you look at every cluster and then you look at the words in every cluster. You count the number of times every word appears in a cluster, and that's called as term frequency. However, you do not stop there. You multiply term frequency with something called as an inverse document frequency. So this makes sure that we put more weight on the words that are meaningful to a cluster, and put less weight on words which are used across all clusters. So then we find this score which is called as TF-IDF score, which is given by this formula, and we find it for all the words in a cluster. That helps us to understand which words within one cluster should be used as keywords to describe that cluster, and that's how we extract keywords from every cluster. So using BERTopic in such a way, this approach is called as the bag of words approach, where we have this TF-IDF matrix for each cluster, and then based on that matrix we look at keywords associated with every cluster. Now here is how the results of this BERTopic actually look like. So here you can see for every cluster there are a set of keywords which are associated with every cluster, which have been obtained from the term TF-IDF matrix. The higher a term is in a TF-IDF matrix, or the higher TF-IDF score it has, the more likely it is to be a keyword for that cluster. And then we can even do a full visualization where we can hover over to each topic, and then we can get the title of that particular topic. So here you can see the orange cluster is everything to do with question and answers. The red cluster is everything to do with language. The red cluster is everything to do with language, but applied in the medical domain. That's very important. So we have reached this stage until now. But the problem is that although we have reached this stage, we are using a bag of words approach. That's fine. But the problem with this approach is that it does not take semantic structures into account while representing a topic. What do I mean by that? What I mean is that when we are looking at a cluster and when we are finding the topic or the keywords associated with that cluster, all we are doing is finding the TF-IDF score, which is essentially a counting scheme. But nowhere are we saying that, okay, are the keywords which we've obtained semantically similar to what the document actually represents? Do the keywords actually make semantic sense? Do their meaning is similar to the meaning what the overall cluster represents? We are not doing anything with respect to meaning. So let's say, for example, let's say I'm looking at cluster number 53 and the keywords are GANs, GAN, adversarial generation, etc. This representation is fine, but I should do one more check, right, regarding whether the words here, whether the keywords here are semantically similar in meaning to the documents in this cluster. That's where I'm encoding some kind of a semantic relationship, and that's where I'm extracting the I'm extracting the main property of text, and that is that words carry meaning. Currently, no meaning is being exploited. So today what we are going to look at is that we are going to look at how to integrate representation models and how to integrate generative models on top of BERTopic. So which means that this 6-step framework which we have seen so far, or rather the 5-step clustering has 3 steps and the TF-IDF has 2 steps. This framework which you have seen, we need to integrate representative models and generative models on top of this framework so that we can take semantic structures into account while representing a topic. That's the main goal of today's lecture. So let's get started with today's lecture and let's dive right into it. Alright, so here's the solution to this problem. What we are going to do is that we are still going to use a bag of words approach to generate a meaningful representation of the keywords. We are still going to use the bag of words approach, but we are going to add one more step on top of this. What we are going to do is that we are going to look at the keywords which have been generated and we are going to tweak the representation or the ordering of the keywords using much more powerful techniques such as embedding models. Now the advantage of bag of words approach is that it is a very fast method. So we will combine this fast method with powerful but slower methods such as embedding models which do contain information about meaning. And what we'll do is that, let's say using the bag of words approach, let's say for one cluster we got that these are the main keywords which should be looked at. So we'll take this set of keywords, we'll do some techniques on this which are representation based techniques such as embedding models, and we will re-rank these keywords so that the order of the keywords now carries information about meaning of which keywords are more similar to the meanings of the documents in that cluster. So what we are going to do is that we are going to re-rank the initial distribution of words to improve resulting representation. What you see on the screen here from left to right, this transition over here is called as re-ranking. And if you observe closely, on the left we have summarization, summaries, summary, abstractive and document. On the right we have summarization, summary, so those two are the same, but after that the order of the keywords has changed. Why has it changed? Because we have learned that abstractive is more similar in meaning to the whole essence of all the documents in that cluster. So we will use these as the final list of keywords when we are going to look at the most important keywords to represent that cluster, right? So this is called as re-ranking. In BERTopic, such re-ranking models are also referred to as representation models. So here, if I were to look at all the steps, I already told you that there are these 3 steps of clustering, right? You embed the documents, then you reduce the dimensionality space by projecting it into a lower dimensional space using UMAP or PCA. Then you cluster the embeddings using K-means, DB-scan or HDB-scan. Then you use a bag of words approach, you create TF-IDF matrix and you have a list of keywords you want to look at. Then you re-rank those keywords in the last step. This is called as fine-tuned representation, or it is also called as adding a representation layer on top of BERTopic or it's also called as re-ranking. This re-ranking is what we are going to look at in today's lecture. I hope you understood the meaning of re-ranking. Why we do re-ranking is that we need to make sure that the keywords which we have extracted actually match the meaning of whatever is contained in the documents, instead of just looking at counts and numbers like what is done in the TF-IDF matrix. Alright, the advantage of re-ranking is that although even if we have millions of documents, let's say, the number of topics or the number of clusters will only be 100 or 150, right? Especially in the example which we have been seeing. So this representation block which I have shown you, this final representation block only needs to be applied once for every topic. It does not have to be done separately for all the millions of documents. We need to look at each cluster as a whole, and then we need to do the re-ranking for one cluster as a whole once. So if there are 150 clusters with 100 million documents, we still need to do the re-ranking procedure only 150 times, which means the process is not as slow as you might expect, right? And so you might be thinking, okay, how do I do this representation? What are the different types of representation models which are available? And that's what we are going to do in this next part of the lecture. Now there are different representation models which are available which you can use, and all of them use different techniques. We are going to look at KeyBERT and we are going to look at MMR. There is also another framework which is called as Spacey. So now, since the BERTopic is so modular, you can even, let's say, use KeyBERT. Let's say you start with KeyBERT and then you say that I am not happy with just one, so I'll stack another block of MMR. We'll look at all these, at what these names mean. But for now, I just want to tell you that the modular nature of this framework is what makes it so much better. If you think KeyBERT is something you don't want to use, you can just replace this full block with MMR, or you can replace it with Spacey without having to change too much of the entire code. So as has been written here, after applying the CTF-IDF weighting, topics can be fine-tuned with a wide variety of representation models, many of which are large language models. So now this fine-tuning can also be done with representative models and generative models, which we'll look at later. Generative models we'll look at the end of this lecture. For now, we are only looking at representative models. And that too, the two main models which we are going to look at today are MMR and KeyBERT, and we are going to see all about what they mean. I hope you have understood until this point. We are basically looking at fine-tuning, which is the process of re-ranking the obtained keywords using large language models. Those can be either representative or generative. So let's look at representative models first. The first type of model which we are going to look at for this fine-tuning or re-ranking is called KeyBERT Inspired. Now, what this model or this framework does is something very simple. Let's say we have one cluster. So if you are looking at this image over here, yeah, let's say we have this cluster in maroon color, right, which consists of a bunch of abstracts. What this KeyBERT Inspired will do is that, let's say we have that cluster and we already have the keywords using the TF-IDF matrix. It will first take all the documents in that cluster, and then it will create an average embedding vector for all of the documents. So this average embedding vector consists of a general meaning of what all the documents in that cluster represents. So what all documents in that cluster represent, and then what we will do is that we already have the keywords and we will embed the keywords. So we'll project each of the keyword into a higher dimensional space. So cat, that, cute, all of these keywords will be projected as a vector. And then what we'll do is that we'll find the similarity between each of these keywords and this embedding vector which represents all of the documents. So see this purple vector here, we are going to find the similarity between the purple vector and each of the keywords. What that will do is that if some keyword is more similar to the general meaning of the documents, it will have a higher similarity score. So it will be re-ranked. It will be re-ranked to a higher position in the keyword list. If some vector such as that has a lower similarity score with the general meaning of the document, then it will be pushed below. You see what we are doing here? We are taking the original keywords and their order, and then we are reordering them based on which keyword is more closer or which keyword is more similar to the general meaning of the document. That's why this is called as capturing the semantic meaning. So this method is as simple as that. We are going to take all of the keywords which we have extracted using the TF-IDF score. We are going to find the cosine similarity between each of the keyword and the average embedding vector for all of the documents in that cluster. Then we are going to re-rank the keywords according to the cosine similarity score. Higher the cosine similarity score, the more preference that particular keyword will be given. So the average document embedding per topic is calculated and compared to the embeddings of the candidate keywords. And this cosine similarity score is then used to re-rank the keywords again. That's the main algorithm, or that's the main sequence of steps which is followed in this KeyBERT Inspired. Another method which we are going to look at in the code is called as Maximum Marginal Relevance, or MMR. This is the MMR which I was talking about here right now. So the reason this is called Maximum Marginal Relevance is that if you look at KeyBERT Inspired, there might be some redundant keywords, let's say language, languages, meanings. All of these are redundant keywords, right? If we need language, why do we need languages? So the main aim of MMR is to reduce these redundancies and filter redundant keywords and only keep those keywords that actually contribute something new to the topic representation. So you can think of this as reducing the overfitting kind of, and only keeping, so reducing the number of keywords and only keeping those keywords which mean different things but are still related to the main document. So in one sentence, what MMR does is that it helps us to diversify the topic representation. And the way it does is that the algorithm attempts to find a set of keywords that are diverse from one another but still relate to documents they are compared to. So let me repeat that. The algorithm will aim to find keywords which are different from one another but still relate to the documents they are compared with. So the way the algorithm does is that it first embeds a set of candidate keywords and then iteratively calculates the next best keyword to add. So it starts with a set of keywords and then iteratively finds which are the next keywords to add. I am deliberately not going into too many details of this process because this is a lecture series on hands-on LLM. So I want to keep the focus more on the practical aspects and the implementation. Soon we are going to come to coding the entire, all the models, the KeyBERT Inspired, the MMR, which I am discussing right now. So when we do this in the code, we'll also need to set a diversity parameter which indicates how diverse the different keywords need to be. So these are the two methods, the KeyBERT Inspired and the Maximum Marginal Relevance. Both are different methods and both re-rank the keywords in a different manner. You can even stack MMR after KeyBERT Inspired, as has been shown over here. You can use KeyBERT and then you can use or then you can choose not to use MMR, or you can just use MMR. The choice is yours. Since this is a modular framework, you can use whichever method of representation or fine-tuning which you seem fit. Now what we will be doing is that I'll take you to the coding interface and we'll code the representation models which we have seen until now. In particular, we'll code the KeyBERT Inspired and we'll code the Maximum Marginal Relevance, and let's see the results as to how it changes or re-ranks the keywords. Here is the Google Colab interface which we are going to use today. So if you look at the pipeline which we are constructing, the first steps until here are the same what we looked at in the previous lecture. So first we have to download the dataset, then convert every document into a vector, reduce dimensionality, cluster the embeddings, then take it to a TF-IDF stage. So that's what I'm going to show you in the Google Colab. I'm going to go through this part a bit faster because we have already covered it in the previous lecture. So these are the packages which you will need today. You will need BERTopic, datasets, OpenAI and data map plot. The reason we need OpenAI is that later we are also going to integrate generative models with the BERTopic. Until now I showed you representation models on the whiteboard, right? We are also going to integrate generative models later on. So you can go ahead and install these packages. It will take around 1 to 2 minutes, I think. Once the packages are installed, the next thing what we have to do is to download the dataset itself. So let me show you the dataset which we are going to download from Hugging Face. This is the dataset which has this list of around 45,000 abstracts and the associated titles with it. So we can download it using the load dataset function provided by the datasets package in Hugging Face, and then we can extract the abstracts and the title from each of the paper which has been downloaded. Then comes the first step. We have to take every document and then we have to encode it, which means we have to convert it into a vector embedding. And here also there is a choice of which embedding to take. So we are going to use this embedding model called GTE small. I have discussed about this in the previous lectures a lot, but GTE small basically takes in documents and converts it into a 384 dimensional vector. So after running this code, you will basically go through this entire process where all the documents are converted into a 384 dimensional vector. The next step, as has been shown over here, is to reduce the dimensionality. So now what we are going to do is that we are going to use UMAP, and we are going to convert the documents or the vectors from 384 dimensions to a 5-dimensional space. These are called as the reduced embeddings. And finally, we are going to use the clustering algorithm. So here we are using HDB scan. You can of course use DB scan. We did not use k-means because in k-means has no provision to deal with outliers. Also in k-means you have to specify the number of clusters from the start itself. So that's a bit of a challenge, and that's why HDB scan is better. And for clusters of different densities, DB scan also does not do a robust job. That's why HDB scan is preferred in this particular case. You can of course experiment with k-means here, DB scan, you can experiment with PCA here. Right, so these three steps have been performed, and then in this step, which is the, let me change to a different color here. So in this step, we have to use BERTopic. We have to use BERTopic and convert documents of each cluster into a TF-IDF matrix, so that we get the ranking of the keywords. So that's what we are doing here. So topic model equal to BERTopic, and here you have to specify three models. The embedding model, which I showed you at the start, which is the GTE small. Then we have to specify the UMAP model, and then we have to specify HDB scan model. Now you see how modular this is. If you want to change to PCA, just change this to a PCA model. If you want to change HDB scan to k-means, you can just change it over here, right? So after you run this, the topic model will be created and our model will be trained. In the previous lecture, we saw that you can use topic model.get topic info to see the main keywords which are associated with every topic. So every cluster will have a corresponding topic name and the representation keywords associated with each cluster. Now let's get to the main thing which we want to do in today's lecture. So until now we have reached this stage where the keywords are there with every topic, but they don't encode any semantic meaning. So now what we are going to do is that we are going to integrate representation models on top of the framework, the TF-IDF framework, what we have reached until now. Okay, so first what we are going to do is to duplicate our model such that we can easily show the differences between using a representation model and without using a representation model, right? So let us duplicate the model which we have created so far and call it original topics. We are not going to change this, which means that these are the keywords associated with every cluster without adding representation models on top of it. Which are these representation models? It's this KeyBERT Inspired and MMR. Okay, now when you add representation models, the topics would change, the keywords would change associated with every cluster. So let's say if we have the original topics and if we have our model. So what we are going to do is that we are going to create a function which is called as topic differences. And what this function will do is that this function will basically tell us the differences of words between the five topics, and we are going to show 5 words per topic. So basically think about this. So let's say I show you this table, right? If I show you this table and let's say I look at the first 5 topics over here and look at the keywords. which are in the original model. When we do the new model, I'll show again the 5 topics and the new keywords so that we can inspect the differences between them. This will show us what the representation models do and why we are using it. So here you see we are extracting the top 5 words per topic, and so in each model, so let's say original model and the new model, 5 topics would be shown, and in each topic 5 words would be shown, so that we can see the differences between both the words very clearly in the two models, right? So let's first integrate the first representation model, and that's KeyBERT Inspired. So from BERTopic.representation, you can go ahead and import KeyBERT Inspired. You can define the representation model to be KeyBERT Inspired, and then what you have to do is that the topic model which you had obtained previously over here, where was it? This topic model which we have obtained previously, we need to update it now. We need to update it with the representation model. So the command to be used for that is that topic model.update topics. And then we have to provide the abstracts, which is our data set. And then we have to provide the representation model. And in our case, the representation model which we are using is KeyBERT Inspired. And then we will call the topic differences function to show the differences between the original model and the updated model, right? So just in 6 lines of code you can run this, and then you can inspect the keywords. So let's say for the original, without adding the representation model KeyBERT Inspired, for the first cluster the keywords were question, questions, QA, answer, answering. For the updated, it's answering, questions, answer, question. Not too much difference, I would say. For the second cluster is speech, ASR, recognition, and acoustic. And here it's phonetic, encoder, language, speech. So here you see we immediately start seeing the difference. Do you see that in the updated, when we integrate the KeyBERT Inspired model, the words are easy to understand first of all, and they make a lot more sense rather than END. END is not related to language or speech or sound at all. ASR also is difficult to comprehend, but phonetic, encoder, language, speech, they are words which make more sense, and probably because we are integrating the semantic meaning. We are looking at keywords which match the meaning of the document, right? So remember what happens in KeyBERT Inspired. In KeyBERT Inspired, what happens is that we look at the keywords and we see which keywords match the meaning of the original documents in that cluster. So here all of these keywords match the original document meaning much better. That's why they are shown, and clearly they make more sense than the original model. And that can be seen in many different, even image, visual, multimodal images. So here captioning is added, which was not there before. So there are some differences between the updated and the original, but it's also important to point out some drawbacks. So in the original, for example, translation, NMT is there, which is an abbreviation which is very useful for people of the field. But when you are comparing the meaning, NMT is maybe not related at all in meaning to the original document. So it's not shown in the re-rank keywords. That's one disadvantage of using KeyBERT Inspired, that it does not know what to do with abbreviations, because abbreviations are semantically not related to the meanings of original words in the vector space. So it does not rank them properly. That's one disadvantage of using KeyBERT Inspired. So there are advantages as well as disadvantages. But I always prefer to integrate an embedding model on top of the TF-IDF, because it just encodes much more information. The second method which we are going to look at is maximal marginal relevance. As we saw, what this method does is that it has keywords, or it outputs or prints keywords which have different diversity to prevent redundancies. So here you see there are a lot of redundancies, right? See summarization, summaries, summary, abstract. Even in the updated model, summarization, summarizer, summaries, we don't need all of these in the keyword because all of them say the same thing. So what maximum marginal relevance does is that, as we saw in the document over here, it diversifies topic representations and it filters redundant keywords and only keeps those that contribute something new to the topic representation. So what we have to do is that we have to specify something which is called as a diversity parameter. In the code, what you can see is that when you run the code for maximum marginal relevance, it's very similar to the code for KeyBERT Inspired. So here if you see, we have to first specify the representation model, and here it's maximal marginal relevance, and we have to also specify the diversity score. So it's 0.5. If you increase it, the keywords will be even more diverse. I think of this as the temperature parameter which is there in the large language model output. So after the representation model is defined, then it is the same thing. Here we use topic model.update topics. Here also we have to use topic model.update topics, pass in the abstracts and pass in the representation model. And then again you can print out the topic differences between the original model and the topic differences between the new model and the original model. So let's look at this fourth document or fourth cluster keywords. In the original model, there are a lot of redundancies, right? Summarization, summary, abstract. But in the updated model, when you use maximal marginal relevance, you see there is summarization, there is extractive, rouge, factual, which means summary is not shown again and again and again, which means that redundancies are avoided. This is a direct application of using MMR, which means that it works. If you even see the keywords which are obtained, they are not very different from the keywords which are obtained in the original model, but I would say the main use of MMR is to prevent redundancies. So many people even use a framework where they use KeyBERT Inspired, and on top of that they use MMR. So then that gives you the best of both worlds. KeyBERT Inspired helps to preserve the semantic meaning between the extracted keywords and the document's meaning, and maximal marginal relevance helps to maintain the diversity in the keywords and avoids redundancies which are present in KeyBERT Inspired also. So this is how you can integrate the representation models on top of topic model. Now this is so modular that you can even add one more topic model dot update topics, and you can add another layer of a representation model on top of it. It's as easy as that. This is the modular nature of BERTopic, which I'm explaining through code. I explained the modular nature of BERTopic through the whiteboard, but now I am explaining the same thing through code. Awesome. So until now in this lecture, we have reached a point where we have seen how representation models can actually be used on top of bag of words approach to encode more semantic meaning between our extracted keywords and how to re-rank the keywords. And we saw the differences between KeyBERT Inspired and MMR, and we saw the advantages and disadvantages of both. Now what we are going to do is that we are going to use generative models on top of the bag of words approach which we have seen until now. So if you look at this diagram, instead of integrating representation models here, we can even integrate generative models on top of the keywords which are generated. So let us see how we are going to do that. To use generative models on top of the BERT pipeline which we have seen so far, we have to define the task very smartly. So let's say we have reached a stage where we have extracted keywords using the TF-IDF matrix approach. What we can do is that we can use generative models to create labels for the topics. So let's say keywords have been generated. Now what, either using just the TF-IDF or using representation models, we can add a generative model block on top of all of this, where we can ask the LLM to look at the documents, to look at the keywords, and based on the above information to give a short label of the topic. What the LLM will do is that it will look at clusters. So let's say there are 1,000,000 documents and 150 clusters. It won't do this for the 1,000,000 documents. It will just look at the 150 clusters. So let's say it's looking at cluster number 1. It will just look at the top 3 documents. It will look at the keywords which we have already found, and then based on these it will find out the label, and then it will do this similar process for all the different clusters. That will really reduce the computational time instead of doing it for all the different documents. In fact, the way BERTopic is coded up is such that it only looks at 3 documents within one cluster, and I'll show you that in code. Now this LLM integration can be done, of course, through 2 types. It can be done through an open source manner using a very powerful generative AI models like FLAN T5, and of course it can be done through closed source models also, such as ChatGPT. First, what I want to show you is that how we can use open source models like FLAN T5 to code uh, the generative model block on top of what we have seen so far, right? So what we have to do is that from BERTopic.representation we have to import text generation, and then we have to give a prompt. So here the prompt which I have given is that I have a topic that contains the following documents. The topic is described by the following keywords, and then I have these keywords here. Based on the documents and keywords, what is this topic about, right? Then I have to mention the generator, which is basically a pipeline created through the transformers package of Hugging Face, and I'll say that it's a text to text generation model, and the model is Google/FLAN T5 small. You can control F or search about this model and you will find it on Hugging Face. You'll see that it's a model based on FLAN T5 and it has small. It's small in size compared to the XXL and other sizes which are present in FLAN T5. If your model has, if your computer has sufficient memory capabilities, or if you have GPU, you can feel free to explore FLAN T5 XL or XXL also. Right. Now, what we have to do next, this is the most important part of the code, the representation model itself. Earlier, when we used representation type models, we used representation models equal to maximal, marginal, relevance, or we used representation model equal to KeyBERT Inspired. But here the way we define the representation model, it's a bit different. We have to do it through text generation. So we have to say that representation model, it's a text generation. So it gives an indication to BERTopic that it's a generative model which has been used. We have to mention the generator. We have to mention the prompt. And this doc length is the maximum length of the characters in the label which we have to generate. This is not the number of documents which we are seeing in a cluster. The number of documents which we are seeing in a cluster is fixed, that's equal to 3. The BERTopic will only look at 3 documents in a cluster. It will have this prompt, it will look at these 3 documents, it will look at keywords, and then it will print out a label with the maximum length, maximum word length as 50. So now what we can do is that one thing which I wanted to show you, here I think the doc length is 50 means the character length. So let's be sure about that. As always, we can take the assistance of Claude. So I'm going to go to Claude chat right now, and I'm going to ask what does doc length mean here, right? And here we can here we can see that the doc length equal to 50 specifies the target length in tokens for the text output. So it's not really words, but it's tokens. So it will generate approximately 50 white space separated tokens, roughly equivalent to words in this case, for the label. So that's the meaning of doc length. Alright, now that that is cleared, so this is the text generation, this FLAN T5 small. One thing which I wanted to show you is the internal working of what exactly happens when we are generating the text. So what's happening is that here is the internal code of BERTopic. So here you can see that it's looking at 3 documents, and what it does is that it looks at the prompt and then it replaces this string called documents with the 3 documents, the 3 joined documents, and then it replaces this string called keywords with the keywords which have been obtained from the topic model. So it will go to the topic model and get the keywords, and in the prompt which we have written, so here you can see the prompt which we have written, it will replace these keywords with the keywords which it extracts from the topic model, and it will replace these documents with the 3 documents which it extracts from that particular cluster. So this is how internally BERTopic works with generation, with text generation models. And I wanted to open up this black box for you just so that you get an understanding of how this code really works. My main purpose here is not just to show you the code, but to actually explain to you step by step how each part of the code is working. And once we define the representation model, the next part is the same. We have to update topics. So here you can see we have the topic model.update topics, and then we can do the same thing, topic model.update topics, and then we can write the abstracts, which is the data, and then we can specify that the representation model is this text generation model. And then again we can print out the topic differences between the main model and the new model, the generative model, and the original topics. So here you can see that I am running everything on my CPU, and it takes around 2 minutes for me, around 1 minute 11 seconds. If you are running it on a GPU, it will be blazingly fast. So let's see. So this is my original topics, and here are the labels which have been constructed by the large language model. And here you can see that the label is question answering systems. Here the label is speech recognition. Here the label is image language learning. It makes sense, right? For these three, at least the labels seem to be related to the keywords. But for this one, translation, NMT, machine, neural, it seems science/tech. Now that's the, I would say, drawback of open source models. They are free, so we did not incur any cost here. But the problem is sometimes the output does not make too much of a sense, right? So now here translation, NMT, machine, neural, it's been labeled as science/tech. It's very generic, does not make too much sense. So this you can use to understand how you can integrate generative models. But now I'm also going to show you how to use closed source models. So I showed you until now how to use open source FLAN T5 models, and now I'm going to show you how to use closed source models such as GPT, and let's compare the performance. With open source models, we saw that the performance was quite good for the first 4 documents, but for the fifth document, the extracted label was a bit generic. Now let's see how ChatGPT API does in comparison. Alright, so what we have done over here now is that everything else is the same. The prompt is exactly the same. The only difference is that instead of using an open source model, we have used the OpenAI client. So here we have to say client equal to OpenAI.OpenAI, and then we have to specify our API key. I have deliberately not written the API key here for privacy reasons, but once you create an account on OpenAI, you will get, I think, $5 worth of free API key credits. So you can copy paste your API key here, and then so here we said that the representation model is text generation, and then we added the model itself, right? But now here the way you have to add it is that representation model equal to OpenAI. So you have to import from BERTopic.representation this module called OpenAI, and then representation model equal to OpenAI. You have to specify the client, you have to specify the model, and you have to specify exponential backoff, etc., so that your requests don't become overloaded. Now, and then here you have to mention the prompt, and then you say the same command, topic model.update topics abstracts, and then representation model equal to representation model. So this command actually stays exactly the same as this command over here. What changes a bit is what you put in the representation model. So here you have to import the OpenAI package given through BERTopic.representation itself, whereas here you have to use the text generation, which is also given through BERTopic.representation itself, but the names of those modules are different. Once you run this will again, it took 1 minute 19 seconds for me, but look at the labels for this. For this one, so for the translation NMT, machine, neural, where it was showing some science, tech, now it's showing improving neural machine translations with, now here it shows Persian question answering dataset, here it shows end-to-end ASR systems, here it shows multimodal image understanding. That's because in the prompt I have written, based on the information, extract a short topic label, and then it puts the short topic label over here. I would say these answers are much more robust than the answers which we obtained from the open source FLAN T5 model. So you always have a choice to use between open source as well as closed source, but here I just want to show you again the modular nature of BERTopic, where we added representation models, the encoding, the embedding models we added before, such as KeyBERT Inspired and MMR, and then on top of that we can add generative models. We can even stack 2 generative models on top of each other just for fun, to show you the modular nature of BERTopic. And I actually encourage you to experiment with all of these variations when I will share this code file with you. Right, and then what you can do is that you can go ahead and plot a figure for all the different um, labels which have been obtained through GPT 3.5, and I'm showing the figure over here. So these are the different labels which have been obtained or which GPT 3.5 actually prints out. This plot has been made using the package called as a data map plot. I was getting some errors making this package, so I have replaced it with a new code, but that also takes a long time to run. But for some folks, even for the GitHub repository associated with this paper, people have been able to replicate this plot. So you can try it on your own machine, but here you can see how beautiful this plot is, where we can see all the clusters and we can even see the names associated with each cluster. Whatever is in gray here, these are outliers, which means these documents are not associated with any cluster. I find it incredible that we started with 45,000 abstracts, 45,000 titles and documents on ArXiV, and now we have condensed it into a cluster representation like this, using everything related to natural language processing. That's pretty awesome. Alright, so this is the figure. We can even make a word cloud, and this is the word cloud for our topic modeling, and which shows the words which appear the most in different topics. And here we can see that PEFT, which is parameter efficient fine tuning. So this is for topic number 17. So we are looking at cluster number 17 here, and then we are looking at the words which appear the most in that cluster of documents. Here we can see that we have parameter efficient fine tuning, LoRa, fine tuning efficient. So this whole cluster seems to be about fine tuning essentially. So you can even do this word cloud visualization technique for different clusters to see which words are represented the most. Alright, this brings us to the end of today's lecture, where we covered a huge number of things actually. We started with this topic of integrating representation and generative models with BERTopic, and we saw how amazing the modular nature of BERTopic is. The modular nature of BERTopic allows us to stack representation models for fine tuning on top of the framework which we have seen so far until this TF-IDF matrix. But we can stack a fine tuning representation model which extracts the semantic meaning between documents, and we saw two such models. The first is KeyBERT Inspired. And the second one which we saw was MMR, right? Then we saw that not just representation models, we can even integrate generative models into this BERTopic stack. We can use open source generative models and even closed source ChatGPT API, and we saw that ChatGPT API performs slightly better than open source Fluent T5. So the whole goal of this series is to show you a huge number of applications of natural language processing, representation models, generative models and large language models, which can be useful to all of you. Until now we have covered a lot of projects. Maybe we have covered around 5 to 6 projects so far, which all of you can start doing and implement it on other datasets as well. My main goal is for you to take these codes and implement it not just on the dataset which I have showed you. So here I showed you the ArXiV dataset, right? You can go ahead and implement this on Reddit dataset or your own. Let's say you have LinkedIn profile, collect your posts and apply the same code and then extract topic models for your LinkedIn posts. Wouldn't that be cool? Wouldn't that be awesome? You'll get to see what you generally talk about the most. Those will be clusters. These kind of projects opens the door for a wide number of other projects which you can use to develop your understanding and then also add to your resume. So try doing creative projects which no one else has based on what you have learned. That will also impact and improve your profile tremendously. I hope all of you are liking these lectures. I look forward to seeing you in the next lecture. Thank you.